Okay, thanks everyone for coming to the first talk. I'm John. I work literally right down the block at GroupMe, which we're like half a block away on 18th Street. And GroupMe is a large and growing mobile chat application. And we want to do this talk to kind of share a little bit of what we've done over the past like 2-3 years to grow our infrastructure along with the number of people using our service. So it's kind of like we're going to talk about, what we're going to talk about is kind of an experience report of what we've done and what we've learned. I want to start with a problem statement, like why are we talking about services? Why does this matter? Why does every conference have at least a talk about services? And I think it could boil down to this sentence. Our Ruby on Rails application is difficult to change. We have some app, it's grown in scope and complexity over the years, and changes have become harder and harder with the amount of people, code, etc. In the beginning, we have this beautifully polished gem. Our application is like a very coherent whole. We've thought through every area of its construction. It's just a pleasure to work on. But as time goes on, it gets a lot less coherent. This is a cover art from a game called Katamari Damacy, and the goal was to build a ball of like unrelated things, and that's what many Rails apps become. It becomes this like mass of things that are like not very related to each other, but all touching each other and all very kind of coupled together. We start using this word monolith. We start calling our app the monolith. The monolith represents all of the mistakes of the past, and when we talk about services, it's the bright, shiny future when we're going to fix all of those problems. I mean, this is really common at every conference. This is just over the last 10 months or something. These are from Confreaks. You have companies like Square, Yammer, Living Social, large companies with many hundreds of engineers talking about how they have some original application, some monolithic application that they are continuing to build and slowly trying to extract services out of it so that they could sort of increase their agility. It's so common in the Rails community that I've seen this term, monorail, kind of thrown around. The first time I saw it was on Jeff Hodge's blog. It's a portmanteau of Ruby on Rails and monolith. It's just so common to continue to throw everything in one application. There's good precedent for this even when you look beyond sort of our community. I mean, this is a quote from Warner Virgils from that 2006 ACMQ article. And here he talks about how Amazon was kind of in the same boat. From 1996 to 2001, when you went to Amazon.com, you were hitting a front-end web application that was hitting a back-end database. And they stretched this as far as it can go. And finally, in 2001, the famous kind of edict came down that you're going to do everything as services now. It's worth noting that in 2000, their type-line revenue was like $3 billion a year. So they stretched their monolith extremely far. So back to our community, a lot of these talks tend to focus on sort of synchronous services. And I think when we think about services, we tend to picture a fleet of small Sinatra applications that all own some vertical slice of our domain that all talk to each other through HTTP. And I wanted to focus on a different type of service, some asynchronous services that we've extracted from our application to scale it out. And when I say asynchronous, I'm really talking about message passing. I'm talking about services that interact with each other by dropping messages onto some kind of medium. So some kind of medium is used in between our services. Messages are exchanged via that medium. And the way I want to talk this through is just talk through some patterns that have emerged from our extractions of these services. We tend to think of this as like, regardless of the tools we're using, there's some interaction patterns between the services. We want to go through kind of some of the benefits of services in general, and then these message-based asynchronous services, some of the operational concerns, of which there are many, and then talk through some of our learnings that we've had over the past couple of years. In terms of patterns, we're going to talk about two. The first pattern is something I've been calling service mailbox. And this is a pattern where we have some kind of medium in between our services, and clients are writing individual messages into a queue. And that queue is then monitored by a service that processes those messages as it can. Now, when I talk about a queue, I'm talking about a Fifo queue. So in terms of the data structure, items come into the queue, and they exit the queue in a first in, first out kind of way. So a queue is going to expose at least two operations, a minimum of two. It's going to have an in-queue operation where you give it an item, and that item is added to the back of the queue. And then it's going to have a complementary dequeue operation, where the first item that's scheduled for delivery will exit the queue and be returned atomically. So we end up with something like this. We end up with our application enqueuing messages into this mailbox, this shared repository, and our service dequeuing from that same mailbox. And I want to talk through this with specific GroupMe features just to give you guys context of sort of how this works. The core of GroupMe is message delivery. So GroupMe is a group chat application. Users join a group, and messages sent to that group are relayed to the other members of the group. We're going to use these UX stencil people as an example. This is the best friends group. If we have a user, Steve, who sends a message to GroupMe, to the best friends group, we will relay that message to the other 3 members of the best friends group. Likewise, if another person replies, we will relay that message to the other 3 members. So very straightforward. It's a one-to-many kind of broadcast group system. We support many different delivery mechanisms to get these messages to users. So primarily, we're doing things like smartphone push delivery, so things like iOS, Android, and Windows Phone. Then at the bottom, we support quite a lot of SMS, different networks and different protocols to deliver messages to feature phones, users who aren't on smartphones. There are a lot of business requirements around message delivery. Because it's our core feature, there's a lot of assumptions about how this should work. The first one is very simple. Messages should be delivered exactly once. We do not want to have a message be sent to the same user multiple times. We don't want duplicates to be delivered. And almost as importantly, we don't want messages to be dropped on the floor. We want to have a delivery guarantee where if a message comes into our system, it will exit our system exactly one time. Messages should be delivered as quickly as possible. So when a message comes into our system, we are focused on having it exit our system in as little time as possible. Finally, we retry and try to deliver messages as we can to fulfill on the first requirement. But if a message is in queue for over 2 hours, we will begin to drop messages. These messages are very ephemeral. Tara's message about the fact that she's heading to drinks might be useful after an hour, but it certainly isn't useful after 15 hours. In the beginning, GroupMe was sort of a 24-hour hackathon project, and we're still working with the same code base that started at that hackathon. The initial kind of prototype of GroupMe was an SMS product. The users were given a telephone number represented a group. Any member who sent an SMS to that number, it would be broadcast to the group. In the beginning, this was done in a very kind of synchronous fashion. These requests would come in from Twilio, the messages. We would then relay them back out to Twilio within the context of a web response request, a request-response cycle. And then, this worked well for a few weeks until GroupMe started to get more traffic. And it evolved in the same way many Rails apps evolve. We backgrounded that work. We wanted that work to happen not in the context of a request-response cycle, but in the background so that we could return to the user as quickly as possible. And this worked very well for a long period of time. We continued to build on this infrastructure using Rescue. We started adding more services, so not just SMS delivery, but push delivery, using things like Apple's APNS or Android's C2DM. Some problems emerged with volume. The first problem was throughput was choppy and low. So Rescue, I'm sure many of you have used Rescue, it's fork-based. So Rescue would, after every job, refork itself, or depending on how badly we had it monkey patched at the time, after a few minutes, or 15 minutes or something like that. This led to very choppy throughput. So we were very focused on getting messages out as quickly as possible, and we had a huge variance in the quality of service an individual message would experience because of our senders kind of constantly stopping and restarting themselves. And as a result, throughput was very low. Rescue was not focused on high throughput. There were lots of different types of jobs in the queues, so we had lots of challenges around throughput. Large number of processes. So because throughput was low on an individual process, we had to have a large number of them as sort of a mitigation. And when you think about a Rails process, a monolithic Rails process, when you're running it, there's a lot that comes with that, right? If you're lucky, your Rails process is something like 150 megs, right, just in the real world. It's consuming things like database connections. There are things that prevent us from infinitely running as many processes as we need. At some point, we need to be more efficient with the processes we do have because there are limited resources supporting those processes. Less operationally, more on the development side, we exhibited different rates of change on our transport service. So we were constantly tweaking the way message delivery worked, doing things like duplicate detection, changing the way we were sort of logging operationally what was going on. It had a very specific rate of change that was very different from the rest of the application. So to solve these problems, we introduced a specific service whose job was entirely message delivery. We called it the transport service. And the transport service is essentially a high-speed event machine rescue worker. And when we were doing this, we were very concerned with trying to make the migration path as easy as possible because it was our first experience with an extraction. We wanted to continue using Redis. Rescue was already using Redis as a job queue, and it was working. It was already in our infrastructure, and we understood it really well. So we didn't want to introduce a lot of new moving parts into our infrastructure. So we built transport service as a drop-in replacement for Rescue. It's this high-speed worker that just kind of sits there, monitors a queue, and delivers messages to the appropriate service. It uses Redis list as a queue, as I mentioned, and it uses Rescue serialization formatting key names. This was the easiest way for us to do the extraction while not creating too much churn in the core GroupMe app itself. And just like Rescue, we're using a list as sort of the shared structure. Messages are pushed into Redis from this GroupMe application, and the messages are popped from transport and delivered as they become available. So a couple of good things about this. Redis provides the exactly once message delivery semantics we talked about. It's pretty easy to achieve that with Redis. Much easier than some other smaller building block systems. And we'll talk more about that later. Higher, more even throughput. So because we were able to create something focused on the specific task at hand, we were able to really focus on making it as fast and efficient as possible. Easy migration path. Because we were very focused on building a drop-in replacement for Rescue, it was very easy to not change anything about how we were producing messages and focus on the consuming side. And then finally, same Redis dependency as Rescue. We didn't introduce any new infrastructure. There was nothing new to learn about. It was the same tools we had been using with Rescue, just extending it beyond one application. So that's one pattern. The other pattern I want to talk about that we use often is something we call event stream. So this is different in the sense that it's not a shared mailbox between a client and a service. This is more about a shared stream of data between all of our services. So in trying to think about a data structure that kind of represents what an event stream is, we'll just talk about like a file on disk because it's pretty common and familiar to everybody. So file exposes a couple of operations. There's a way to append data to the end of a file. So we can take some data, put it onto a file, and then it'll become part of that file immutably. And we'll have some kind of operation to read from that file. So we'll be able to get from the file some data, some amount of bytes from a given offset, right? Just like a file on disk. And the way we think about this is we have some kind of shared stream in the middle of our services. And at the top, we have things publishing data into that stream. And at the bottom, we have things reading from that stream. And the stream could be anything from click data from a website, what are people clicking on, to user events that are happening within our networks, to basically anything, operational data and analytics. So I want to talk through in a specific feature again, just like message delivery. We have a news feed at GroupMe, just similar to any other kind of social application. And it has very different characteristics from message delivery in terms of requirements, in terms of durability, and in terms of delivery time or real-timeness. So we'll go back to the best friends group and talk through an example. At GroupMe, we have a feature where if you find a message that you think is funny, you can like it to indicate that you approve of what that person said. Once you do that, a push delivery is sent to the user who sent the message originally, and we keep a counter of how many people liked it. At the same time, we also make a note in your newsfeed of who liked your message with what the message was and show you the avatar of the last person who liked it. So pretty standard stuff. In the beginning, this was a very sort of like easiest thing that could possibly work Rails thing, right? We had a controller, we rendered some data depending on what was in the database. We made queries in real time. This worked for a while. It started to bend pretty quickly. These were very slow database queries. After a certain amount of user sort of growth, it became very hard to serve these queries in any reasonable amount of time. Once our data set kind of like grew beyond what could be held hot in database cache and page cache, it became very hard to service these queries within anything that wasn't like a few hundred milliseconds or seconds. More importantly, these requests were competing for database time with things that we did want to be real time. So things like message delivery, which is very important for us to be as real time as possible. The newsfeed was competing against that. So overall, everything was getting slower because these reads were all sort of in the same bucket. And finally, it was unnecessarily real time. It was real time because that was the easiest thing that would work, but it wasn't necessary. So we introduced a service, just like transport service. We introduced something that we called, cleverly enough, newsfeed service. And its job is to assemble and serve the newsfeed. We're using a tool called Apache Kafka for this event stream purpose. And we'll talk a little bit more about what Apache Kafka is. Its dynamics are very different from Redis, and it's sort of a different tool for a different job. So in this case, we have services. We have a couple different services in our network. We have the original core GroupMe application, a message service, a relationship service, all publishing data into Kafka. So as users take action when they form new relationships, when they send messages, when they like messages, that data is written to Kafka as an event. This event stream is then monitored by this newsfeed service, which reads that and creates newsfeed items as necessary. So a little bit about Kafka. So it's a distributed high-throughput pub-sub messaging system. It's a project from LinkedIn, and it exhibits the same characteristics as a file. You can kind of think of it as a file. Messages are appended to a topic by a producer. So a producer gives Kafka some bytes that it then appends to this large stream. Consumers iterate through the topic started at a given byte offset. So a consumer will say literally, I want byte, 1,000, a K of bytes from offset, Y. And Kafka will deliver that information to the consumer. You can kind of picture it, so it's like a large log file that any service on the network can write to or tail from. You can kind of think of it as like a shared log file. So in this case, we're publishing user events to this event stream. Just lazily, we are, in the background publishing events as they occur. And the newsfeed service will create content from these events where necessary, where it is appropriate. So Kafka is multi-consumer. So like I was saying before, we have multiple consumers down below. So multiple things could be reading from that queue at any given time, which means that a message could be delivered more than once, right? Potentially, if those were the semantics you were after. It's also rewindable. So in theory, if you had enough disk, you could store all events that occurred on your network from the beginning of time and go back and rewind and replay those events on different services. So we'll talk about some of the benefits of these approaches and some of the nitty-gritty about how they actually work. Then we'll talk about some of the operational concerns and some overall learnings that we've had. So scalability, this is something that people talk about a lot in services talks when it comes to sort of going from one Rails application to something that's more smaller and more granular. I mentioned this before. Each process consumes a uniform number of resources, right? Like we talk a lot about infinite horizontal scale, but it's kind of a lie, right? There's always some barrier, right? It's never infinite, truly. And the limit is much lower than you would think, right? It's what we've learned anyway. Things like database connections are actually a valuable resource. If anyone's, if you're using Postgres, every connection to Postgres is going to be a forked process on Postgres. And after a couple hundred of those or a few hundred of those, you top out completely, and you just can't add any more processes. Having smaller building blocks allow us to add targeted capacity. If we need 16 senders and its job is just to deliver messages over HTTP or over SIP to some third party, it doesn't need a database connection, and we can focus on what the job is that service needs to do. The services scale individually. We can then target where we need capacity and kind of turn the dials in a very granular way, instead of just having one unit of this is GroupMe and it's either on or off. Agility is another thing we talk about a lot when we talk about services. If anyone read Paul Dix's service-oriented design book, there's a chapter where he kind of goes through all of these. The nice thing about services is that we could deploy updates independently. So rates of change differences across our services, it doesn't, we don't have to spend a lot of time planning change and coordinating change alongside other developers working on other features. The units are small enough where they're individually deployable. When it comes to asynchronous services, because we have this messaging layer in between a lot of our services, deploys are very low impact. Right? We have this natural buffer in our network that will absorb data as our services kind of come back to life after a deploy. The reusability, the nice thing is any component that needs to send messages, we can just point it at that same shared queue or that same event stream, and they can simply start injecting messages into that queue very easily with very little coordination with other components. Cheap experimentation. This is one that isn't talked about as much, but that we found to be very helpful. Certainly with anyone who's worked in a larger company, you'll find that like data ownership silos tend to evolve. So as services get built, as people start building components for a company, you'll find that that knowledge or that data gets very siloed amongst a certain group of people. And getting at that data becomes an exercise in having meetings and drawing design documents. And Conway's law is something else we talk about a lot when we talk about services. Melvin Conway said organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. So if you have a team with 3 sub-teams and you're building a system together, you're likely to get 3 different systems with 3 different ways of talking to each other. It's just, naturally what happens. As the communication's bifurcated, people go in their own direction, and then when they come back together, it's a lot of duct tape and glue. Publishing to event streams really helps mitigate these silos. If you start your project and you say on day 1, all interesting, whatever you define as interesting in your business, all of that data gets published into this event stream, you don't have that problem. You have access to the data at any time. If you just figure out what a notable event is and publish it, it becomes very easy to sort of take that data and do something unanticipated with it. So experimental projects could start using that data in like ways that were not necessarily foreseen when that data was produced or when that data was started to be captured. So in our case, we could do things like, since all components of our service are publishing this newsfeed data into Kafka, we can then spin up very, very easily projects that can use that data experimentally. So if we wanted to reuse the likes data in a different way, like show a leaderboard per group of who liked what message, we can do that without building like a complicated ETL process between the newsfeed database and this other database. We just point it at Kafka and start reading from the stream. It just reduces the coupling between teams. Teams now have a uniform interface for dealing with each other and dealing with each other's data. And it solves a lot of problems. LinkedIn talks about this a lot. Before they started using Kafka or started developing Kafka, they had lots of these like little lines in between services and lots of little one-off ETL processes. Now that they have sort of a central data pipeline, they're able to kind of dip into the stream, use the data in any way they want, and dip out very quickly. So yeah, and data availability removes barriers to exploration. If that data is available and a developer can say, well, I want to hack on this little pet feature I have, they can do that with real production data and without impacting any other movement going on the other teams. Okay, so back pressure. This is something that's important to us and probably pretty important to anybody who's dealing with third parties. And when I talk about back pressure, I'm talking about artificially limiting the rate at which we do something. So we have some amount of work to do, and we want to artificially limit how much gets done in any given second. And the reason this is important to us is that some of our partners mandate a maximum delivery rate. They say, look, you can only send us 100 messages in a second, or you're going to unintentionally DOS us. And we have to govern our rate across all of our delivery partners. And having these message-oriented services helps us do that in a way that we couldn't do with Rescue, for example. So message-based service boundaries are natural buffers. So again, we have this natural buffer in there to kind of soak up work. GroupMe's load is pretty bursty. So for example, sporting events, we see large spikes of messaging traffic that have to be absorbed somewhere in our network. These messaging buffers are the place where we tend to absorb the load and then slowly parcel it out and deliver it at whatever rate we're able to deliver it. So I talked about our messaging service being sort of an event machine worker. We threw up a generic component called GroupMe Pace, which is the guts of what we use for message delivery. And it's just an event machine worker that listens on a queue and can be used to do certainly like I/O heavy tasks, things that are like delivering messages over HTTP. And Pace was built with back pressure in mind because we had these requirements. So in Pace, we can do things like say, you only deliver 100 jobs a second. We could programmatically pause and resume service from Pace just to ensure that our throughput is even and expected and we're not delivering huge surges of traffic to our partners. So we automatically back off on failure. If a failure occurs, we can detect that and stop delivering. We can just put everything on pause so that we don't add to the problem. So we detect failures and we just stop delivering. We back off. So if the third party is having trouble, if their load is pegged or something is occurring on their side, we can just back off and take our traffic out of the equation. And like I said, messages are buffered in the queue and flushed when the system stabilizes. So because we have these buffers, it's very easy for us to absorb that load. There's lots of operational concerns here. So like, for example, we can't buffer infinitely, right? We have limits, and certainly the services where we're using Redis, there's a pretty clear limit, which is the memory of the system. So we have to monitor it pretty closely. In real life, it doesn't really matter because we never have multi-hour outages, and if we do, our TTL of 2 hours tends to prune the queue, but it's definitely something we're very conscious of. Okay, then finally, interoperability. This is another one of the kind of classic benefits that people talk through. But it's been surprising to us how often this has really come in handy. I'm going to talk through one other component of our system. So this is a diagram of how a message is received via SMS through one of our SMS partners. And they're using a protocol called SIP. SIP is a telephony protocol for VoIP that has a small messaging component. And we have to have something listening for new SIP messages, and we then have to inject it into our system. So these messages come in, we have a daemon that listens and just listens for these messages, normalizes them, puts them into a service mailbox in Redis, and then we have a worker process that just monitors that inbox and delivers the messages. So all of the business logic of what is a GroupMe message lives in the consumer, and the SIP receiver its surface area is very limited to how do I receive a message over SIP. And it turned out that when we were building this, the easiest way for us to prop up a SIP receiver was to use Java. There was a tool set there, thanks to Google, that made it very easy to prop up this service. But because we were thinking about how do we have these things interact in a kind of an asynchronous way, and we had already been using Redis in this fashion, it was very easy for us to limit the scope of that SIP receiver just to what it was good at. So we took the bits of Java that we needed, and we scoped it to deliver a message, normalize it, put it onto a queue, and then all of our very specific business logic lives in Ruby, which is much more of our home turf. Okay, so concerns. So there are lots of things now we have to think about that we didn't have to think about before when we had a single sort of application. I want to talk through monitoring first. So we spent a lot of time trying to figure out how do we monitor this new system that we're building? What are the things that are bellwethers to show us that a problem is occurring somewhere in our infrastructure? And we look at a couple different metrics. The first metric that's really important to us is quality of service. And this is the quality of service is when an action is initiated, how long does it take for the result to occur? So for example, for message delivery, when we get a message, when a message comes into our network, how fast can we turn that message around and deliver it to our messaging partners such that a user can see it on their phone? We take the time that the message exits and we subtract it from entered, and we monitor that. So in this case, when a message hits the border of our network, we stamp it immediately, whether it comes in through SMS or through HTTP. We capture a timestamp, and we pass that timestamp through our network. So wherever that request goes, we pass the timestamp along with it. When the message exits our network, we then take that timestamp and capture it. So in this case, we will do some quick math, take the two timestamps, and come out with a quality of service. This quality of service indicates everything in between the user sending the message and the user on the other side receiving a message. We graph this and watch this pretty closely, and it varies from partner to partner, and there's some just table stakes latency from our kind of network working through our routing infrastructure. But this is kind of our key metric that we think about. We think about it with the newsfeed too. It's a lot less important in terms of business requirements, but it's something that this is how we kind of think about service quality. Queue size is another thing we look at, but queue size is kind of a weird metric. So with Redis, we very simply we look at the size of the list. List size is the queue size. That's how many messages are pending delivery or processing by a service. This is often 0 unless failures have occurred and we're applying back pressure, which is kind of interesting because a non-zero queue size doesn't necessarily indicate a problem. So we watch this number pretty closely, but it doesn't in itself tell the entire story. This number, along with QoS, is how we kind of monitor for failure. Okay, another concern that we have, and I've talked about this a couple times now, delivery guarantees. We're very explicit about when a message enters one of these systems, how often will it be delivered, right? What are the guarantees we're making about this message? Because we're using very small building blocks like Kafka and Redis, a lot of this is on us to define and to guarantee. We're not using a large-scale messaging broker that makes a guarantee to us. We are on our own in most cases. So, these are the three kind of guarantees of the way we think about them. A message could be delivered at most once, which means 0 or 1 time, exactly once, which is the only one, and at least once, meaning it could be 1 or more. And we think about this in the sense that when we're designing services, if there's a chance that the semantics, the delivery guarantee we're going to aim for is at least once, then we have to think about idempotency. We have to think about if a message is processed more than once, what are the side effects? And can the side effects be contained such that only the first delivery actually has a side effect? So business requirements drive this for us. We think about what are the requirements of the specific feature, and those dictate how we put the building blocks together to develop a guarantee. Interface synchronization has been another challenge. Because now we have multiple services speaking the same language or speaking the same interface, we have to make sure those interfaces and those messages are guaranteed to be the same on both sides of the queue. One approach that we've used that's been pretty useful for us is being very explicit about the value objects that represent a message. So we'll have actual Ruby objects that represent a message that are serializable that can be used and shared code used on both sides of the service, such that a client can use those objects, serialize it, put it on a queue, and the service, when it takes the message off the queue, will inflate it into this value object. Consumers and producers work with the same object, and this enforces a consistent interface. These clients are shared via a gem, which is versioned along with the service. We'll keep the code with the service and test it along with the service. Initially we spent a lot of time agreeing on hash-based JSON contracts on both sides, and immediately got out of sync. And we'll talk a little bit more about that too. Another thing we think about in terms of service design at GroupMe is failure modes. We very consciously think about what happens when a component fails, because these components fail all the time. The behavior of your system during failure. So when a component of your system fails, when Redis is unavailable, when the transport service falls over and can no longer deliver messages, what's the behavior of your system? We try to avoid cascading failure. So we're very conscious of the fact that if everything's talking to Redis and it's a shared resource, and Redis doesn't have exactly the easiest high availability kind of setup, right? They're working on, AnyRes is working on Redis Sentinel, but that's probably a long time away from being production ready. So we tend to think of Redis as okay, this may go away. How will our system react when Redis goes away? So when Redis is unavailable, or when memory fills up, right? When we buffer too much and Redis just tips over. This is also something that could occur. We think about things like if a new message comes in and Redis is unavailable and we can't deliver it, what is the right behavior? There are many options, right? We could return an error to the user and tell them to try again. We could accept the message and buffer it in memory and wait for Redis to be available. We could drop it on the floor. And thinking about this very explicitly has helped us build resiliency into the system. Durability is related but slightly different. Durability is about when a failure does occur, how much data loss or how much queue loss can we absorb? And this has a significant sort of side effect on performance. So balancing durability and performance, what is the right trade-off to make for the given piece of infrastructure? So by default, Redis isn't very durable, right? I think the default configuration is something like every 60 seconds it'll do a RDB background save if 1,000 keys have changed. But if you're using Redis in this way, you only have a couple of keys changing, you may never trigger one of these background saves. Even with AOF and replication, message loss is still possible, right? There's always gaps. Unless you're doing an fsync after every change, you're probably going to have some level of exposure. And then on the Kafka side, Kafka, for example, doesn't acknowledge messages as they come in. So messages from a producer, it's a one-way protocol where messages come in, and Kafka never says, okay, I got your message, cool. Or, hey, we didn't get an acknowledgement, we're going to retry. So there's exposure there too. we try to think about this very specifically because we have lost these systems before. So for example, with the newsfeed, if we lose messages, it's fine. There's no business requirement to ensure durability on those messages. But message delivery is a whole different beast, and we have to take time to construct the service to reduce the possibility of message loss to the smallest risk factor possible. Okay, so that all said, I want to talk about some high-level learnings that we've had going through the process, some of the things that we've taken away from it, kind of all over the map from things like how we construct these services and how we think about them operationally. So the first, you can go a long way with your monolith. Amazon went 5 years with their monolith, and now is the probably most sophisticated, services-oriented business on the market. The three talks I'm talking about, like Square, Yammer, Living Social, these are large-scale businesses that do real levels of traffic. So the art is to figure out when does it make sense to introduce complexity like this into your network or into your system. And there's no one-size-fits-all answer, but the pragmatic approach of sort of spending as much time with your monolith as you can and sort of really making a move only when you really feel that pain, I think certainly seems like the right kind of trade-off, right? Because otherwise you're going to spend a lot of time building services for something that maybe has little or no traction or no users. Messaging is a tool for service-oriented systems building. So we're web people. Many of us came from web backgrounds. I think when we have a problem where we want to get two systems to communicate, TCP/80 is sort of the default way we go. We think, okay, we're going to use HTTP between these services. It's well understood. Messaging is an alternative to this. There are many other alternatives. Messaging is one alternative. So there are alternatives. Web services is just one way to kind of tackle this problem. Background work is a prime candidate for service extraction. So when we're thinking about what is it, how do we slice up this application, where do we begin, things that you're already doing asynchronously are very easy extraction points. And looking at that work and identifying the pieces of infrastructure that have a different rate of change from the rest of your application and have growing complexity requirements. So, for example, our transport service grew in complexity to the point where a message had relationships with other messages in the system. Rescue really wasn't, Rescue's very sort of, each job is its own brain. It's very designed for individual delivery. It was a clear extraction point for us. Many people use Rescue for things like welcome emails and et cetera, and there's probably, it varies from application to application, obviously, but definitely looking at what you're already backgrounding and targeting those for extraction is a good starting point. Service extraction provides many of the promised benefits. So everything people talk about, we've seen benefits from going this route. We've gotten the benefits of individual scalability, the isolation and testability of each individual service, the robustness of each individual service and monitoring, the ability to kind of monitor in a very granular way what a service is doing. There's a lot of upside to kind of biting this work off and going down this path. But as with all things engineering, there are many trade-offs to consider. You have to make them to realize these benefits. You now have a lot to worry about. You have systems that are talking to each other across a network that's not guaranteed to be available. You have queuing systems or database servers that have their own operational characteristics that you now have to keep in mind. You have business logic maybe that's spread across different systems and needs to be kept in sync. You have testing challenges because your nice Cucumber acceptance test that runs through your entire stack will be very hard to maintain in this world. And in fact, we don't try to do large acceptance testing across both applications. We are very focused on the interfaces between the applications, and that's where we focus our testing. You must explicitly plan for failure cases. You must be very explicit about understanding what happens in your system when components fail. Failure is another mode of operation. It is not exceptional to have two services on a network that can no longer talk to each other. It's something that's going to happen very often. We talk about this a lot at GroupMe. The system must bend but not break. We want to ensure that any given failure will bend the system. We may degrade service, we may slow down, but we won't snap, we won't break. And it's taken a lot of kind of explicit planning and battle scars to get closer to this. You won't know how broken something is until you measure it. There are many things going on in your system, and as you distribute it, there are many more things going on in your system, and without measuring those things explicitly, you'll never know how badly, what kind of shape you're in. Things like quality of service. When we started measuring that, opened our eyes to latencies that were just hiding in our stack. This is kind of a digression, but one of the things that we talk about a lot are percentile slices rather than averages. Looking at data as an average tends to hide some of the extremes of that data series. You look at this. This is a cartoon. The caption there says, or the sign there says, average depth 3 feet, and this gentleman has fallen into a hole of 6 feet. When you look at things in an average, you don't know how bad it is at the extremes. Things like New Relic, RPM, when you look at that first graph, that's an average graph. That is not telling you the whole story. We look at the average, but we also look at things like the 95th percentile of all requests, the median, the 50th percentile. That just means we take the data, we sort it, and we take the 95th sample or the 50th sample. This was a hard lesson that we learned. You will have to experience system failure to build resilience into your system and to your team. You will have to fail. You will spend a lot of time explicitly planning for what happens during failure. You will deploy your services, and then you will fail in half a dozen new and unexpected ways. There's a paper called How Complex Systems Fail by Richard Cook, who I think is a professor at the University of Chicago. And it's just a bunch of bullets about how failure occur in large systems. And when he talks about large systems, he's talking about like real deal large systems like healthcare, transportation, triage, hospitals, things like that. So when he talks about system failure, he's talking about the patient not making it. And it's funny because there's a lot of parallels to what we do, even though the stakes are quite a bit lower. And this point I like a lot. Failure-free operations require experience with failure. To rid your system of the potential of unexpected failure, you have to fail. You have to earn those battle scars. And it's another lesson we've learned. We prefer smaller building blocks like Redis and Kafka over message brokers like RabbitMQ and Cupid. This is just our personal preference. We spend a lot of time evaluating different systems. A lot of message broker systems have lots of complexity and lots of requirements in them. We found that the flexibility of using smaller systems has helped us kind of adapt to exactly what we need to do rather than crafting our requirements around what a broker can do. Focus on the interfaces between your systems. That's the important bit, right? How do your systems talk to each other? What are the messages that go between the systems? We focus on this a lot. We tend to focus our testing here. We tend to think about the way services interact by what are the actual messages being passed through, and being very explicit about protecting those messages against change. So lots of people use like versioning system like Avro, which is a messaging format system from Apache. That's what they use at LinkedIn to sort of guarantee a contract between systems. We're not doing that. We're using JSON, but we're trying to enforce the contracts through code. And it takes a lot of explicit thought to get here. Ad hoc JSON serialization formats are fraught. You'll hate it. If you try to do it on both sides, you will blow it. We blew it a lot. Building small value objects and making it very explicit and testing those objects on both sides, both your client and your service, makes it such that it's much harder to make a mistake. From our Perl heritage, this maxim still applies. There's more than one way to do it. This is one way. This is one thing that we're doing. There's many other approaches that could be taken, but focusing on services this way has helped us a lot in terms of managing our operational complexity. Your mileage will vary. You will make new and interesting mistakes over trying to extract services out of your application. But certainly some of this will likely apply. That's all I have. Thank you so much. Appreciate it.